Okay, let's get back to the second derivative test. So the test states this: have a function f of multiple variables with a scalar value function with its first and second partial derivatives continuous in a neighborhood around a point A. And at that point A, the gradient is 0. So we have a critical point. So for H being the Hessian, it has to be invertible, so the test is conclusive. We have these three outcomes. F is a local maximum at A if the Hessian at A is positive definite. It's a minimum. It has a minimum at A if the Hessian is negative definite, and it has a saddle if the Hessian is indefinite. So we won't go through a proof of this, but the idea of the proof is this. If I do the quadratic approximation at A for f of A plus h, so some perturbation, some point near A, it looks like f at A plus the gradient of A dot h plus 1/2 h transpose times the Hessian times h, right? But I know that the gradient is 0 at A because we're at a critical point. So all I get is something that looks like this. So what does it mean when h is positive definite? If the Hessian is positive definite. So the Hessian positive definite means that this term is positive, which means, let's see, so that means, let's call this term whatever, y. Y is positive, which means f at A plus h is equal to f at A plus some number, some positive number, y, which is greater than f of A. So it's a minimum, right? F at A is a minimum. All the points near it are larger than it. Instead, if h is positive definite, then y is negative. So all the points near it, f plus h, are f at A minus y, or I guess this is say plus y. Now this is going to be less than f at A because I defined y as negative, which means that f at A was a max. I hope that makes sense. And if I have some points that are greater or less, and that's the definition we gave of the saddle point. There are some points near it that are greater and some that are less than the value at A. Okay, so let's practice finding local minima, local maxima, and saddle points. So we'll practice on this function here. I have this function of 3 variables. F of x1, x2, x3 is a scalar valued function. The first step is to find the critical points, and for that I need to find the gradient and find the x's that make it equal to 0. So the gradient of f. So the derivative with respect to x1 is 2x1 minus, 1 from that term, minus x2, and that's it. With respect to x2, minus x1 plus 2x2 minus 1. And with respect to x3, 3x3 squared minus 3. Now I want to know when that is equal to the 0 vector. So we know that it should be x3 cubed, not cubed, x3 squared minus 1 is equal to 0. So that means x3 should be plus and minus 1. For the other two equations, I have 2x1 minus x2 is equal to 1. And minus x1 plus 2x2 is equal to 1. So if I add those equations together, I get x1 plus x2 is equal to 2. And if I subtract them, I get 3x1 minus 3x2 is equal to 0. So I get x1 minus x2 is equal to 0. So putting those together, that means that x1 and x2 both have to equal 1. So the critical points that I find are 1, 1, 1, 1, 1, negative 1. To classify these, I can use a second derivative test. Classify with second derivative test. So how do I implement that? I find the Hessian, I plug in these points, and I check if it's positive or negative definite by looking at its eigenvalues. So let's find the Hessian. We'll keep the gradient on screen here for a second because that'll be helpful. Okay, so H is going to be a 3 by 3 matrix. So I need to do the second derivative with respect to x1 twice. So just a 2 from here. I'll do the derivative of this guy with respect to x2 is -1, with respect to x3 is 0. The derivative of this guy with respect to x1 is -1, so symmetric, good. With respect to x2, it's 2. With respect to x3 is 0. And there's no x1 or x2 in the third equation, but there is an x3. The derivative of that is 6x3. Okay, so now we have two cases. At 1, 1, 1, H equals 2 minus 1 minus 1, 2, 0, 0, 6, 0, 0. So what are the eigenvalues? Lambda minus 2, 1, 0, 1, lambda minus 2, 0, 0, 0. Lambda minus 6 is the determinant I need to set equal to 0 to find the characteristic equation. So I have just this term in the third row and column, so it should be lambda minus 6, although, okay, plus, minus, plus, minus, plus. So it is a plus sign times the determinant of this block here, lambda minus 2, 1, 1, and lambda minus 2. So lambda minus 6 times lambda squared minus 4 lambda plus 4 minus 1. So lambda minus 6, and this is a 3. Lambda minus 3, lambda minus 1, right? These combine to get a 3, which I factor as minus 3 and minus 1. Awesome. So I set this equal to 0. So the eigs are 1, 3, and 6, all positive, implies that the Hessian is positive definite. And by the second derivative test, this implies that 1, 1, 1 is a local minimum. I hope that makes sense. I'll let you think about it for just a second. Okay, and then the next step is just to do the same thing with the other critical point. So I move this up here and make sure you can see it. Oops, over here. So now at 1, 1, negative 1, the Hessian is 2 minus 1, 0, minus 1, 2, 0, 0, 0, and minus 6 because of the minus 1 for x3. And so the determinant really looks the same, except I get an x plus 6. So the characteristic equation, I'll kind of skip some of these steps, is x plus 6, x minus 3, x minus 1. Hopefully it's okay to skip those steps. The only thing that changes is the sign of this 6 here, which implies the eigs are at 1, 3, and minus 6, which implies H is indeterminate. So 1, 1, negative 1 is a saddle. Or I guess we should say F has a saddle. F, or let's say a saddle of F and a local minimum of F, because those are properties of this function. Awesome. Okay, so that is scalar valued functions of multiple variables. What about vector valued functions with multiple variables? This more general case, right? So now let's consider that we have f, which is a function of n inputs, so x1 to xn, and it has m outputs. So f1 through fm, m functions. So now the idea of the derivative is not a vector, it's a matrix, the Jacobian. Jacobian is defined like this. So the ijth element is the partial of fi with respect to xj, and I can also write it in terms of these gradients here. I can think of it as stacking the gradients. So let's think of an example of how we can use the Jacobian to write an approximation for the value of a function, right? All of this is about finding approximations, and we're going to eventually take it back to Newton's method where we find approximations of roots. So let's let f be this vector valued function, and I want to find this linear approximation here. Before we had a scalar valued function, it was f of a plus the gradient of f at a times h, or dotted with h. Now it's the Jacobian, and it's a matrix multiplication. And let's consider this actual function here, this f1 and f2, and let's approximate the value of f somewhere near -3 and 0 using a linear approximation, and we can compare it to this exact value here. Okay, so the first thing that we're going to need to do is find all these partial derivatives and stack them up like the Jacobian, right? So let's see. So let's put it in the terms of our linear approximation. So a, the point that we're going to approximate around, is -3 and 0. And h, the perturbation, is going to be 0.01 when I add to -3 to get -2.99, and then 0.01, which is what I add to 0 to get 0.01. Awesome. Okay, the linear approximation says that f at this point, -2.99, positive 0.01, this is approximately, or this is, I say, equal to first, a plus h, which is approximately f at, and I'll write in a this time, 3 and 0, plus the Jacobian at -3, 0, times h, 0.01, 0.01. Make sure you can see that. Whoops, just off screen. Okay, great. So all we need to do is find the Jacobian and plug in. So the Jacobian, let's see, the partial of f1 with respect to x1, 2x1 plus x2 cubed. The partial of x1 with respect to x2, which is the 1, 2 term here, is going to be 3x1, x2 squared. The partial of f2 with respect to x1, 6 x1, x2, and the partial of x2, or f2 with respect to x2, 3 x1 squared minus 3 x2 squared. Great. So the Jacobian at -3, 0 is -6, 0, 0, 27. Looks like that. Okay. So let's multiply all this junk out. So f at the point we're looking, approximately So f at minus 3, 0. If I plug in minus 3 squared is 9, plus 0, minus 9. And then f2 is 0, 0, minus 4. So 0 and minus 4 plus the Jacobian, minus 6, 0, 0, 27 times 0.01, 0.01. So that is 0 and minus 4 plus, put my page number there, minus 0.06, 0.27, 0.06. There we go. So this is minus 0.06, and then minus 327. So it should be what, 73? That looks right. Okay. Oh yeah, and then I compare to the actual answers up above, and it's like pretty close. You can imagine how useful something like that is if you had to do something by hand, right? I mean, that would be an incredibly hairy calculation to do by hand. Okay, so that's how I do a linear approximation. And now let's say, just the value at any point, but let's think about trying to approximate a function, a vector valued function at a bunch of zeros. Now you can start to see how we're getting into Newton's method. So we're on page 9 of the notes. Let's consider a nonlinear system of n equations and m unknowns. So I had and n unknowns, sorry, a square system. So f1 to fn, all functions of x1 to xn, and they're all equal to 0. So I can write them as this, in this vector equation. F is equal to 0, where I stack up all my functions. So can I derive Newton's method for finding this root? Just to understand how this relates to the calculus that we've done so far, when are we going to try and find when a vector valued function is equal to 0? Well, it's when we're trying to solve f is equal to 0 to get critical points. So that's when we would do something like this mathematically. And the idea is that I want to do that to find critical points of multivariate scalar valued functions. And so I'm going to learn how to do it using Newton's method. Okay. Or I will learn how to approximate these roots, which are actually critical points of some other function. This is some other f, so this is y. Okay. Hopefully that motivation makes sense. Okay, so let's derive Newton's method, just as we had for scalar valued functions. Now for a vector valued function, if I'm given just the same as before, some initial condition, right? Some x star that approximates the root here. Okay, so let's define an iteration. Let's say, so I have an initial guess, x naught. Oh, sorry, did I say the initial guess was x star? X star is the equilibrium. That's going to be the solution, the root that I'm looking for, but x naught is my initial guess. So let's assume that xk is somewhere reasonably close to x star. And now these are both vectors. So I know that 0 is f of x star. Gotta write all these arrows this time. And I, of course, can add and subtract xk, right? So this is x star minus xk plus xk. Fine. But then I can think of xk as the point I'm iterating around, and x star minus xk, since it's small, as h. So this now is approximated by f of a, which is xk, plus the Jacobian at xk times h. x star minus xk. So basically the same as we had for the scalar valued function, just a multivariate analog. So we need to know that J is invertible. Let's assume that J of x star, let's say that we assume that J of xk implies that J of x star is invertible. So nothing wonky happens with eigenvalues as I zoom into this approximate function, that I don't have eigenvalues that go to 0 and make some problem with the invertibility of this matrix. This is similar to these other assumptions you had to make throughout the lecture, that functions are fairly well behaved. So hopefully you're okay with the assumption that both the Jacobian at xk and x star are invertible. If that's the case, then I can solve this for x star. Right, I can multiply by the inverse of J. So 0 is J inverse f at xk plus x star minus xk. And then x star is going to be xk, oops, no star here, sorry, minus J inverse f at xk. J inverse at xk. So I don't know what x star is, but the idea is I can define the iteration be xk plus 1 is xk minus J inverse at xk f at xk. So this is Newton's method for multivariate functions. Okay, so what that says, it's very similar to what we did before, right? The Jacobian is the idea of the derivative. Before we had x of k plus 1 is equal to x of k minus f of x over f prime. So now my j to the negative 1 here is like dividing by the inverse. And so the assumption that j is invertible is like saying, assume that the derivative was non-zero. So maybe we'll put a note actually here. This is an analog to saying f prime non-zero in scalar Newtons. Right, the scalar Newton's law, Newton's method doesn't work when your derivative is 0 anyway. Okay, excellent. So that's Newton's in general. And so let's try and use it to approximate some numbers. Okay. Here we go. This guy, make sure you can see it. Okay, so here's the example. Let's try and find all the places where f of x is equal to 0, where f of x is this vector valued function here of two variables, x1 and x2. So first step, let's use MATLAB to visualize these curves. So these, I can think of these actually as level curves in 2D. I'm going to look on the set -5 to 5 in both x1 and x2. And so you'll see it in the PDF in color, but this plot looks like this. So it looks like there are 4 intersection points. And why are we looking for places where the curves intersect? Well, this is going to be this level curve where this is equal to 0 is going to, sorry, where this is true is where this is equal to 0. Where this is true is where this is equal to 0. And so I need both of these things to be true. Well, they're only both true at their intersection points. So intersections, I'll say here, geometrically, we're looking for the intersections where both bivariate functions are true. I'll put a star so you know up here which bivariate functions, these ones with the star. Okay, so let's just start. We say, let's do it by hand and then we'll do it in MATLAB. So step 2 says there appears to be an intersection by -3, 0. Let's see, yeah, this one here, right? Work out by hand the first step of Newton's method, apply to this initial guess, and in particular, calculate x1. Okay, so let's work that out. So if these functions look a little bit familiar, it's because if you go back to page 8 of your notes, the functions here were the same as the functions that we're looking at for their intersection. And then the starting point here is somewhere actually close to 3 and 0. So that looks familiar. That may be why. Okay, get the paper lined up. All right, so how do we find this approximation here? The first step of Newton's. So the first step of Newton's is that x1 should be x0 minus the Jacobian inverse at x0 times f at x0, right? So let's let x0 be -3 and 0. So f at x0 is what? So I have -3 squared is 9. Oh, we actually did this in our previous case, right? So 9 plus 0 minus 9, so 0 and -4 is what we should have here. Great. And then the Jacobian at x0, we already found the same way, right? This is -6, 0, 0, 27. And I'll write here, this is from page 8 of notes. Oh, let me make sure you can see that. Yeah, okay. Great. So what's the inverse? It's a diagonal matrix, so that's really easy. So it's -1/6, 0, 1/27. Excellent. Okay, so let's just find the first step here. So x1 is x0, 3, 0, oops, not plus, minus -1/6, 1/27 times f of x, 0 minus 4. So 3, 0 minus 4/27 minus 4/27 and 0. Oops. Oops, sorry, -3 is our x0 actually. So the answer is -3 and then 4/27 because of the 2 minus signs. So that's some vector. Those are some numbers. So here's what I'm going to do. I'll stop the video now and then I'll do a new video where we get to part 3 of this, which is use Newton's method in MATLAB to find the 4 solutions. So we'll confirm that this number is right, and then we'll find approximates for those 4 roots. All right, see you in a minute.